Here is Yang Bo. He'll tell us about Anyon dynamics.
Yeah, thank you very much. So if you cannot see my cursor, do let me know. Okay. Hi, everyone. Let me first thank the organizers for this very amazing event. So today I'm going to talk about my recent research in Anyon dynamics in fractional quantum Hall effect. So here is the outline. I'll first talk about some things I think many of you are familiar with, this so-called... yeah.
If we're still looking at your title, so okay. You may want to try to reshare the screen.
Share my desktop, maybe. Can you see my slide now?
Yes. Yes.
Okay. And I think you can see my cursor as well, right?
Yes.
Okay, great. Okay, so yeah, so these so-called conformal Hilbert spaces are basically the subspace of a single Landau level with a conformal symmetry. It's a good representation of the conformal group, as well as more importantly, the bulk edge correspondence. So some of the examples are the null spaces of the familiar pseudopotential model Hamiltonians, and they can also be spanned by Jack polynomials. And I'll also talk in a little bit more details on a more general way of constructing these conformal Hilbert spaces from the so-called local exclusion conditions. These spaces are useful because they offer rather clean and rigorous way of defining anyons as a topological object from the truncation of the Hilbert space. And next, I'm going to talk about some of the interesting dynamics of these anyons with two simple examples. One is the Laughlin phase in the lowest and second Landau level. The other one is the nematic fractional quantum Hall effect. I will show that dynamics of these two systems can be fundamentally connected by the fractionalization of the Laughlin quasiholes, which can lead to a BKT-like transition at finite temperature for the low-lying excitations within the same topological phase. And I also discuss about possible ways of seeing this fractionalization of quasiholes in experiments. And in the end, I'll talk about some of the interesting aspects of the anyons by proposing a way of bosonizing anyons in 2 dimensions due to the fact that we have a bulk edge correspondence of these conformal Hilbert spaces. They also lead to a large family of single component bosonic fractional quantum Hall phases, which are basically the dual description of the familiar fermionic topological phases. Okay, so here is the schematics of some of the examples of the conformal Hilbert spaces coming from the null spaces of these familiar pseudopotential Hamiltonians, the 2-body and 3-body and even 4-body pseudopotential Hamiltonians. So this is the full Hilbert space of a single Landau level. And as an example, this is a null space of a V1 plus V3 2-body interaction, the Laughlin 1/5 phase, which is a subspace of the null space of V1 pseudopotential, which in turn is a subspace of the Hafnian, the null space of the Hafnian model Hamiltonian. The other example is the null space of the Moride Hamiltonian, which is a subspace of the 4-body Fibonacci, a null space of the 4-body pseudopotential for the Fibonacci state in the Rizzai series. So every one of these Hilbert space corresponds to a particular type of anyons. And in principle, we can calculate the many-body wave functions of these anyons, from which we can compute the charge and also the braving properties. Okay. These are so-called conformal Hilbert spaces because they do satisfy conformal symmetry as well as the bulk edge correspondence, where the highest density states or the ground state in each of the Hilbert space has the entanglement spectrum with having the same counting as the quasiholes states in the same space in the thermodynamic limit. Okay, so the model Hamiltonians are good ways of constructing these conformal Hilbert spaces. They're more general in some sense to the Jack polynomials because, for example, the Hafnian states are not Jack polynomials. But there is a more general way of constructing these conformal Hilbert spaces with bulk edge correspondence, the so-called local exclusion conditions, which was proposed by myself and my collaborators a few years ago. This is actually a rather simple way of understanding fractional quantum Hall effect in a general manner. What we are asking here is that if we're given a quantum Hall fluid, what happens if we have some constraints on what we can or cannot measure from this quantum Hall fluid? So each constraint can be given by a triplet of non-negative integers n, e, and nh. Basically, it says that if we have a circular droplet containing n magnetic fluxes, so its area is around 2 pi n LB square, then a constraint is saying that if you do a measurement in this circular droplet, you can never measure more than Ne number of electrons and NH number of holes. So this is a rather classical constraint on the reduced density matrix of the quantum Hall fluid. And it turns out all the valid states satisfying this LEC condition span a particular conformal Hilbert space corresponding to a topological phase in the fractional quantum Hall effect. So by valid state, that simply means, for example, on the spherical geometry, these states have to be the eigenstates of the total angular momentum operator. So it does offer a very simple numerical way of generating the ground state and quasi-Hall states of even very exotic non-abelian topological phases. But the key message here is that this particular constraint on what you can or cannot measure on a quantum fluid is really the only physical input you need to define the topological properties. So for example, here I'm listing all the topological properties you can think of from a particular fractional quantum Hall states, and they can all be unambiguously determined by the simple physical input I have just mentioned. And in particular, for all the fractional quantum Hall states that we can define using the model Hamiltonians, all of them can be constructed using the LEC. They correspond to a unique set of LECs. And even for many of the conformal Hilbert spaces or topological phases that can be uniquely determined by the LEC, and even though they cannot be uniquely determined by any model pseudopotential Hamiltonian. And in the spirit of LEC, we can actually see that they can allow us to reinterpret those model Hamiltonians in a rather different way as a von Neumann lattice of the local projection operators. So here is an example when an LEC condition is 323. Basically, it says that for any circular droplet containing 3 magnetic fluxes, you can never measure more than 2 electrons and more than 3 holes. This is kind of trivial. This LEC corresponds to the Moore-Reed phase. And we can, in some sense, impose this locally by a projection Hamiltonian, giving an energy cost for 3 magnetic fluxes when the droplet, when you have 3 electrons in this droplet. And we can construct a von Neumann lattice of these local projection operators, and 2 things that can be proven analytically. First of all, this Hamiltonian, even though it has a lattice form, it does not break translational symmetry in a single Landau level because the lattice constant is on the order of the magnetic length. Secondly, we can prove it is really identical to the 3-body pseudopotential Hamiltonian, which is the model Hamiltonian for the Moore-Reed state. This can be done for many LEC conditions, especially for the entire Reed-Rizai series, but it's not true for any LEC because after all, LEC is more general than the model Hamiltonians. But it does imply for many fractional quantum Hall states, we can really understand it as a continuous version of the AKRT model in 2D, which could be useful because for the AKRT model, we have an analytical proof of the gap for the ground state in a thermodynamic limit. So this could lead to some interesting ways of understanding the incompressibility of the model Hamiltonians in the thermodynamic limit in a more analytical way. So there are some discussions about it in this paper as well. So why are we interested in these conformal Hilbert spaces? Because they are the one way of understanding how topology emerges from the truncation of the Hilbert space. So if we have the full Hilbert space, of course, the elementary degrees of freedoms are electrons. But if you confine ourselves to a single Landau level, removing other degrees of freedoms, for example, for the integer quantum Hall effect, then we are really dealing with quasi-particles that are no longer point particles anymore, but they do carry the same charge and spin as an electron. But if you go further and reduce our Hilbert space into a conformal subspace, then the elementary degrees of freedoms are anyons carrying a fractional charge and, of course, non-unusual statistics. And this, of course, can be physically realized if the interaction gives the energy punishment to the complement of these conformal subspaces. And these anyons are the ones that we are interested in here. And let me illustrate this using the first example, which is the Laughlin phase at filling factor 1/3. So if we have a model Hamiltonian of the Haldane pseudopotential V1, then we know the null space is spanned by the ground states and the quasi-holes, and by definition, it's equal to the null space of this particular Hamiltonian. But if we move on to the more realistic interaction of the Coulomb interaction in the lowest Landau level, the low-lying excitations and ground states are no longer identical to the null space of V1, but they are very, very close quantitatively, as we can see from the wave function overlaps from the numerical analysis. On the other hand, if we go to a second Landau level Coulomb interaction, then the ground state and the quasi-hole states from the exact diagonalizations are no longer living in this null space of V1. The overlap is particularly for the quasi-holes can be very bad, and even for the ground state, I think for not too big systems, ground state overlap is around 60%. Right, so the two, quantitatively speaking, these two Hilbert spaces are quite different, even though, of course, we still believe that we are living in the same topological phase. But what is interesting is that we have very strong numerical evidence to show that these exact states from the Coulomb interactions in second Landau level almost live completely within the null space of the Gaffnian model Hamiltonian, which of course contains the null space of the V1 Hamiltonian. So if you look at the overlap, cumulative overlap of these states within this Hilbert space, the overlap is actually very high. Even though the dimension of the Gaffnian Hilbert space is only a very small fraction of the dimension of the entire Hilbert space, as you can see from here. And in a thermodynamic limit, the dimension of this Gaffnian, the null space of the Gaffnian model Hamiltonian should have a measure 0 as compared to the full Hilbert space. If you look at the energy, it tells the same story. So we can diagonalize the Coulomb interaction within the full Hilbert space. So these black lines are the energy levels from the diagonalization in the full Hilbert space. We can also diagonalize this with the same Hamiltonian in the null space of the Gaffnian model Hamiltonian, and the energies are given by these blue crosses here. And you can see that they are actually agreeing with each other quite well, especially for the low-lying excitations. This is for the ground state, this is for a single quasi-hole state, and this is for two quasi-hole states. But if you look at the variational energy of the Laughlin quasi-holes, then they're really very high up. So the null space of the Gaffnian model Hamiltonian really captures the low-lying excitations, not only for the second Landau level Coulomb interactions, but for a wide range of interactions that we have studied. So the statement here we can make is that for these realistic interactions, as the low-lying excitations are no longer quantum fluids of the Laughlin quasi-holes, but we can still understand them as the quantum fluid of the Gaffnian quasi-holes because they live in the null space of the Gaffnian model Hamiltonian. So let's study these Gaffnian quasi-holes in a little bit more details. So let me just go through some of the basics. So we're going to use a spherical geometry where a single particle orbitals are shown here with a magnetic monopole at the center of the sphere. So when we represent many body wave functions, we use the second quantized form. The string of numbers here from left to right corresponds to the orbitals from the North Pole all the way to the South Pole, where 1 means it's occupied by the electron and 0 means it's not occupied by the electron. Of course, for valid states, they have to be the eigenstates of the total angular momentum operator. I'm going to use the Jack polynomials to describe the states. You don't really need to know the technical details of the Jack polynomials. I'm going to give you a very physical picture. But the string of number you see here is just the root configuration representing the ground state or the highest density state in the Gaffnian, in the null space of the Gaffnian model Hamiltonian. It's a repetition of 1, 1, 0, 0, 0 because the filling factor is 2/5. Now, if we add a single magnetic flux, for example, at the North Pole, what we are doing here is adding a 0 here, and it creates two Gaffnian quasi-holes, each carrying a charge of 1/5. And we can keep adding magnetic fluxes in here until we reach a filling factor of 1/3. And this is the ground state for the Laughlin phase at 1/3 filling factor. And you can understand this ground state as a quantum fluid of Gaffnian quasi-holes. And these circles are representing the Gaffnian quasi-holes here. Now, if I add another magnetic flux in the Laughlin ground state, then I'm creating an additional two Gaffnian quasi-holes, and we can reinterpret it as, of course, a single Laughlin quasi-hole represented by this triangle here. Okay? So the moral story here is that we can really understand a Laughlin quasi-hole as a bound pair of Gaffnian quasi-holes. So the natural question to ask is what can happen if we pull these two Gaffnian quasi-holes apart from each other. And that's what we are doing here by trying to pull one quasihole from the North Pole all the way to the South Pole. When you're pulling the two quasiholes away from each other, you're not going to stay in the null space of V1 anymore, right? But we're still staying in the null space of the Gaffinian model Hamiltonian. And what happens is that when you pull the two quasiholes apart, you are creating these Laughlin neutral excitations. And the further the two quasiholes are apart from each other, the more neutral excitations you are creating in between them. And you can even plot the density distribution when you pull the two quasiholes apart. And since we have the model many-body wave functions here, we can try to understand the interaction between the two Gaffinian quasiholes. So if we look at the variational energy of those states, then obviously if you use a V1 interaction, then the further the two quasiholes are away from each other, the more neutral excitations you are creating here, each one of them costs a finite amount of energy. So this is what you see, where the energy of the pair of Gaffinian quasiholes are increasing with the distance between them. So this is almost like asymptotic freedom, where the Gaffinian quasiholes can be understood as a quark. And Laughlin quasihole is a bound state of two quarks, and you don't see the quark because when you put the two Gaffinian quasiholes away from each other, the further they are away from each other, the higher the energy cost of the state. And these Laughlin neutral excitations are analogous to the bosonic gluons mediating the interaction between the two Gaffinian quasiholes. On the other hand, if we look at the variation energy of V3, it's the opposite story. So V3 actually prefers the two Gaffinian quasiholes to be separated from each other. And even for V5, it's the same thing, just to a lesser extent. So V1 punishes Laughlin neutral excitations, that is obvious, but V3 favors such excitations energetically. Okay, since in the higher Landau levels, we do have a longer range interaction from Coulomb interaction with a more prominent V3 and V5, then this implies a possibility where a Laughlin quasihole can be fractionalized at the second Landau level. Of course, there has been so far no experimental evidence of seeing a fractionalized Laughlin quasihole carrying a charge of 1/6 at second Landau level, probably because this interaction still favors a bound state. But let's keep this in mind for now. And I'm going to switch gear a little bit and talk about the nematic fractional quantum Hall effect. So for this kind of systems, we're not really looking at how to define the topological indices, but are trying to understand how robust the topological properties are in the presence of dynamics, where there is an interplay between emergent geometry and topological order. And these are the concepts first proposed by Haldane back in 2009. And the nematic fractional quantum Hall effect is an interesting example. It was first discovered in experiment 10 years ago, where you see the plateau forming at 1/3 filling factor in second Landau level, showing a topological order, but you also have an anisotropic transport for the longitudinal resistivity. And what is more interesting is that this anisotropy is enhanced at lower temperature, indicating some kind of quantum phase transition. So this is an example with a coexistence of topological order and anisotropic transport. It's not an easy experiment, I suppose, because there has not been many results reported in here, but nevertheless, from a theoretical point of view, it's actually a very interesting question. So here is the spectrum numerically on the torus for 1/3 filling factor with V1 interactions, where you have a ground state here, of course, which is gapped by a dipole excitation at the rotor minimum consisting of one quasi-particle and one quasi-hole. But as you go to the long wavelength limit of this elementary branch of excitations, the quasi-hole and quasi-particle will merge to form a quadruple excitation in the long wavelength limit. And this quadruple excitation is believed to be responsible for the nematic fractional quantum Hall effect. And the main message is that quadruple excitations and dipole excitations are really two different types of excitations in fractional quantum Hall states, because dipole excitations define the charge gap, because you're creating a quasi-hole and quasi-particle that are very far away from each other, but the quadruple excitations give you a neutral gap in the long wavelength limit. Okay, so the natural question is how tunable are these two energy scales in a topological phase, since we do see possibilities of this nematic fractional quantum Hall transition. So we have done a microscopic calculation to show some of the results analytically in this particular paper. So for the neutral excitations in long wavelength limit, we can calculate the gap in a thermodynamic limit given some input as well as a dispersion. So I'm not going to talk about the details of this equation, but one important results we can see from the calculation is that the quadruple excitations of the Laughlin state are exact zero energy states of the Hafnian model Hamiltonian. And the dipole excitations are actually coming exact zero energy states of the Gaffnian model Hamiltonian. So this allows us to construct a toy model or minimal model to understand the transition from a fully gapped Laughlin phase to a nematic fractional quantum Hall phase, where we have the Hafnian model Hamiltonian and V1 and V3 tuning the dispersion of the entire branch of the neutral excitations, as you can see from here. Okay, but what is interesting is that if you look at the model wave function for the fractionalized Laughlin quasi-Hall, this can be shown. If you know LEC, it's actually very obvious, but you can also check it explicitly that this is also an exact zero energy state of the Hafnian model Hamiltonian, which implies, which implies that we can use this same model to describe the transition from a bound Laughlin quasi-Hall to a fractionalized Laughlin quasi-Hall. As we have shown that V1 prefers the two Gaffnian quasi-Halls to be bounded, while V3 prefers the two quasi-Halls to be separated. So it's really about the strengths of these two in this minimal model to decide what you can see for the low-lying excitations of the quasi-Halls. So it's also a competition between the dipole excitation gap and also the neutral excitation gap in the long wavelength limit. In particular, this implies the neutral gap in the Laughlin phase really gives the energy cost of the quasi-Hall fractionalization. Every pair of neutral excitations of gluons between the two Gaffnian quasi-Halls has an energy cost that is given by the neutral gap in the long wavelength limit. And that's how the two things can be connected in a more systematic way. It also allows us to calculate the possibility of this transition from bound Laughlin quasi-Halls to fractionalized Laughlin quasi-Halls. So assuming we have a density, a particular density of fractionalized Laughlin quasi-Halls, then the average distance between the 1/6 charge, which comes from the fractional Laughlin quasi-Halls, is proportional to the inverse of the square root of the density. But this distance also tells us how energetic this pair is, because the distance is proportional to the square of the distance. The square of distance is proportional to the number of neutral excitations in between, and each neutral excitation costs the energy, a unit of energy coming from the neutral gap in the long wavelength limit. And this allows us to calculate a critical temperature at which there will be a finite density of the fractionalized Laughlin quasi-Halls, which depends on two quantities. One is the quadruple gap or the neutral gap in the long wavelength limit. The other one is the magnetic flux density when you tune the magnetic field away from the center of the plateau for the Laughlin phase. That's how many fluxes you're inserting into the Laughlin ground state. Right? So if you want to see the 1/6 charge coming from the fractionalization of Laughlin quasi-Halls, the temperature at which you are measuring has to be larger than this TC, but of course it has to be smaller than the charge gap. Otherwise, you do not have a topological phase anymore. So in principle, we want TC to be small, not large. But this is possible because we know in experiments there's a high possibility that we do see this nematic fractional quantum Hall system where delta 2 supposedly has to be very close to 0, at least smaller than the temperature. Right? So if this can be very small, TC can be small, and this regime in principle can be accessed. So this is really describing a phase transition of low-lying excitations at the same filling factor, which may have interesting experimental consequences. Okay, so how much time do I have? So I have a few minutes. Let me just talk a little bit about this Anyon boson duality, which is basically a scheme of bosonizing anyons or fermions in 2 dimensions for the conformal Hilbert spaces or the fractional quantum Hall effect. So logic is actually pretty simple. We know Luttinger liquids can be 1D Luttinger liquid can be bosonized, and the edge of the quantum Hall fluid is a chiral Luttinger liquid. But we also know because of bulk edge correspondence, an insertion of flux creates either, you can think of the flux as either a quasihole excitation or an edge excitation. And since we can map the disk geometry to the spherical geometry where we do not have any boundary, then these bulk excitations in 2D in principle can also be bosonized. And these quasiholes can be either fermions if they're quasiholes of integer quantum Fourier effect, or they can be anyons or non-abelians if you're looking at a particular fractional quantum Fourier state. So what we can do is to select a conformal Hilbert space, look at the highest density state as a vacuum, and from which we can insert fluxes to create all the other states. Right. The key thing is to interpret each flux as a spinor with total spin S equals to Ne/2, where Ne is the number of electrons. And this is independent of the number of orbitals or number of fluxes you have inserted in. And what we can do is to look at the relative angular momentum or eigenstates of these quasiholes, and then we can tell if they are bosons or fermions. For example, for two quasiholes, two fluxes, its relative angular momentum can only be even, then it's a boson. If it is odd, then it's a fermion, right? We can generalize this to any number of the relative angular momentum of any number of fluxes. And this can be done. And what we do is, what that shows is that if we have a particular ground state consisting of any number of electrons, then we insert n QH number of quasiholes, then this Hilbert space can be mapped to a bosonic Hilbert space containing n QH number of bosons and Ne+1 number of orbitals. And these are the many-body states describing the quasiholes, abelian or non-abelian, doesn't really matter. And we can always find these coefficients of linear combination to form a product state that is in every sense bosonic, where Mi is the number of bosons in the I orbital where I goes from 0 to Ne. So that's really, this is something that can be derived either analytically and in practice, sometimes you have to do numerical calculation because it's a very long analytical calculation. Okay, so that also means we can bosonize fermionic fractional quantum Fourier states. Yeah, so for example, if you have Laughlin state 1/5, as long as it's living in an abelian conformal Hilbert space, like Laughlin null space of Laughlin 1/3, then we can bosonize this to give a bosonic fractional quantum Fourier state. We can also bosonize this particular fractional quantum Fourier state in a different abelian fractional quantum abelian space. For example, the full Landau level Hilbert space to give you a different bosonic fractional quantum Fourier state. Another example is a Morley state, which it is non-abelian, but as long as we are bosonizing it within an abelian conformal Hilbert space, we also get a bosonic fractional quantum Fourier state. But if we have a Laughlin state that is abelian, we can't, either abelian or non-abelian, we can't bosonize it within the Morley null space, because this null space contains parafermions like Mariner fermions in addition to the bosonic mode. And the consequence is that not only can we map the states, we can also map electrons between interactions between electrons to interactions between bosons in the dual picture. And what we gain is that now we're not dealing with anyons anymore, we are dealing with bosons. So they are simpler particles in some sense. But what we pay is that the interaction is a linear combination of many, many pseudopotentials, even though they can decay when the number of n-body pseudopotential becomes large, for example. Because when you do this mapping, the interaction has to capture the original statistical interaction between anyons. So this way allows us to construct a microscopic Hamiltonian that captures the statistical interaction between anyons and even non-abelians. And we can even diagonalize this Hamiltonian in a bosonic space. This is an example where we are bosonizing the Laughlin 1/3 phase for the fermionic case, and the spectrum really looks exactly like, very much like the fermionic case with 18 bosons and 11 orbitals corresponding to a filling factor of mu equals to 2 and shift of 2 as well. Okay, so one last thing I want to mention is that even for the same fractional quantum Fourier phase, we can bosonize it within two different Hilbert spaces, leading to two different bosonic description, each with its own microscopic model Hamiltonian, even though they are the dual description of the same fermionic phase. And the bosonic phases occur at different filling factors as well. Okay, so I guess that's the end of my presentation. So this is a summary. Basically, the main message is that the anyon dynamics can be quite interesting even for the simplest fractional quantum Hall states. And anyons can be bosonized in general. And we should also think a little bit more about the roles of conformal Hilbert spaces and also these bosonic fractional quantum Hall phases. And there are some conjectures about the nature of these, and I'm happy to discuss about those later on. Okay, so let me also acknowledge my collaborators, Zlatko Papic, Ajit Baran, and Wu Yinghai, as well as my students, Tron and Yuju, who are also studied to contribute to some of the work that I have been presenting here. Okay, thank you very much for your attention.
Okay, thank you, Bo. And okay, so now we have questions. Dima, I think, was first.